Well, hello everyone. It's Sunday afternoon here, and I thought I would just get on and do a little stream here with upgrading my vintage ZX81. This is the computer this is the first computer I ever bought when I was a kid. Saved up all my money for this. This computer I think was $100 when I bought it. It's supposed to come in kit form, but when I got it, there was a letter with it that said, "Sorry, we don't have any more kits available. We've given you a fully assembled one," which probably was a good thing because back then I didn't really know much about soldering. I knew how to do it, right? But I was kind of messy, and I probably would have just messed this thing up. So it's probably good that I got an assembled one. This computer is the only computer from my childhood that I have saved. Uh, all the others have come and gone. In some cases, I've rebought them and are now part of my collection, but this is actually the original one. So I'm really kind of fond of this computer. Um, as you can see, there's not much to it. It has a flat keyboard. Kind of got to press kind of hard on these keys in order to register them. And if you look closely, you see also the keys have multiple symbols on them. So like this, well, let's go over to this P key here. The P key here not only stands for P, but it also stands for print. And it stands for quotation mark, and there's a little something written underneath it. I think it says tab, and depending upon the context of the line that you're typing in a basic program, the what it types changes. You can also use things like the shift key, and there's a function key over here to change exactly what it types. In some cases, some of these keys also can display some rudimentary graphics characters. So what are the specs of this machine? When I bought it, it was a 1 megahertz. I think it was one. No, probably 3 megahertz Zilog Z80 processor. But it was the equivalent of a computer like the Apple II as far as the speed goes. In fact, you'll see in a moment here just how slow this thing is. So it has a processor. It had 1 kilobyte of memory, which I later upgraded to 16 by attaching a RAM pack onto the back side of it. So the thing that would fit onto the back of it, it would stick up a little bit. It was called the backpack, and it expanded you to 16 kilobytes of memory. And you could program it in the basic programming language. This is the old school basic language with things like, print and goto and if then and other stuff like that. You could also program it in assembly language, but it was kind of difficult to do so. It didn't have a built-in assembler. So you had to kind of assemble the program yourself by hand, figure out what the machine code instructions are, the numbers are, and then use a command like a peek or poke in order to put your program into memory, and then you could run it from there. So what we're going to do today is, well, first of all, this little computer, before I get onto that, this little computer, over the years, it's got some problems with it. There's a couple of main problems. One is it was designed to hook up to a television. So when you hook this up, it would transmit on either channel 2 or channel 3, maybe a switch on the back. So you could change which channel it would display on. Hook up your television and then tune the television. I'm making a little dial motion here because you would flip, that's the way you tune televisions. There was a dial on the front. They went usually from 2 to 13. Or if you're in different parts of the world, it might go from 1 to 13. But anyway, there was a dial on the front. It would click into place, and you'd tune it to either channel 2 or channel 3, and then it would display the image on there. These days, it's hard to find a television that can tune channels, and it didn't produce a perfect video signal. So today's digital televisions have a lot of trouble picking up the signal out of this and displaying it correctly. So one of the first things that people with these old computers do is they modify it so that it will display at least to a composite monitor. That's the kind of monitor that's got the yellow cord on the back of it. It's not tied to a specific television channel. It's just a video signal. It's essentially a TV video signal, but not for a specific channel. So it's easier to find monitors that can accept composite signals, and but you have to modify it in order to do that. And the other thing I've done to this is I've increased the amount of memory up to 32 kilobytes, and I've also replaced one of the chips inside of it with a modern replacement so that it can, first of all, produce the composite video signal, and it also fixes some bugs that were in the original ROMs of this computer. So why don't we, before we do too much, why don't we just hook this up to a television, hook this up to a monitor, and see what it looks like. So I'm going to get my video cable here. This yellow cable right here, and I'm going to hook that up to the computer. So let me go and hook that up right there, and then I got a power cord to plug in there. And this also uses kind of a standard headphone plug for power, and the reason for that was cost savings. That way they could use 3 of the same plugs on the side instead of 2 and then 1 different one. What that means, I had to like make up a little adapter that would adapt from the standard barrel connectors we use today to this, kind of headphone style plug. All right, so plug that in, and now the computer's on. Doesn't make any sound. There's no speaker in this thing. Actually, the computer itself doesn't make any sound. So what I'll do now is I'll turn on that monitor, and then I'll switch the camera to look at it. So let's turn it on, and there we go. Now, when I flip the video over, you're going to see a lot of lines on it, and that's just, there we go. That's just caused by a mismatch between the rate at which the picture is being displayed on the monitor and the camera that's picking it up. So I apologize for all the waviness there. What I see on the monitor is a nice, steady, black and white image. And one day I'll get what's called an upscaler or a scan converter, and that'll take the composite video signal and then convert it into a form that a modern camera or modern device can use. So it basically takes composite input, converts it to HDMI, digitizes it, and then they can go straight to your computer at that point. So here's how you would have typed in a program back in the day. So, a basic program, the first program you might type in is like something, just print something on the screen. So you start every line with a line number. In this case, I'm going to use 10 as the first line number. And then I'm going to hit the key here that has print labeled right above it. So I'm going to press that key, and then the word print just appears, and then Shift P to make a quote mark, and then let's put in hello. Notice I gotta press pretty hard to get these things to register. And there's no exclamation mark on this. This computer did not have an exclamation mark in its character set. So this is as best we can do. Hello YouTube, and I'm going to press new line, and there's my program up there, and then I'll press run, enter, and voila, there's your program. And let's see, I'm gonna do list, so we can list the program, and then I can do like 20. This is how you did a loop back then. 20 go to 10, which would just cause it to do line 10, come down to line 20, and then go back to line 10, and just repeat line 10 over and over again. So run, and just zips down the screen like that. Now, most computers back in the day, you would have run a program like that, and it would just go forever, right? Because it would just print out hello YouTube, and then do that over and over again. The Sinclair had a way to detect if that was happening in your program, if it was just going to a loop just infinitely around, and it would just stop it. Let's replace line 20 with 4x equals 1 to 10. This is a loop that counts from 1 to 10. Now I've just replaced 20 with a new line 20. And then 30, I'll print out the value of x. And then line 40, I say next x. So that does a for loop that counts from 1 to 10, prints out the value of x, and then loops back and keeps going. So we'll run it, and you can see just how slow this thing goes. And this is not, this is partially a effect of the processor. The processor was not that fast, but also the basic interpreter here is also not that fast. And so things like loops just take a long time. You notice when we did the goto, it went pretty fast, but when we do the for loop, it goes a lot slower. It's because for loops are just slower to do. Anyway, so as a kid, what I would do is I'd go to the bookstore and I'd go out and buy a book or a magazine that had programs in it. This one's called the ZX81 Companion, and inside of it are things like listings for simple games. Over here, you would just open up the book and start. Let's see if I can get that. If I can get this close enough so you can see. Here we go. Close enough to start typing in the program. Keeps going on to the next page. The programs are not that long because you don't have very much memory. A program like this would have taken maybe 2 kilobytes of memory or so to run in. So, and typing on this keyboard is painfully slow. So I'd say, once you got good at it, it would still take maybe half an hour to type this in, just because it's such slow going, and you're kind of like holding the book in one hand and trying to work the keyboard with the other hand, but you got to hold down shift occasionally, so you need a third hand to hold down the shift key. But then, hopefully when you type the program in and ran it, you get a simple little game. This is called Duck Hunt. You're shooting at ducks that appear on the screen. And then if you then remove the power to your computer and turn it back on again, the program will be gone. So if you wanted to save this program, you would hook up an old school cassette player, put in a cassette, and then I think on here you would press, where is it? You press, there it is, save, and then give it a name, press enter, and then it would send an audio signal out to the cassette player. The cassette player would record that audio signal, and then when you wanted to reload the program again, you would just type, where is it? Load, right there, press enter, rewind the cassette, of course, to the beginning, play it back, the audio would come into the computer and it would interpret that audio as the ones and zeros for the program. So the sounds that it makes sound kind of like old school modem sounds, with high, low pitches for your ones and zeros. So that's how you saved and loaded programs back then. Of course, it was horribly unreliable. Probably if you was loading a program, there was probably a 1 in 3 chance that it wouldn't load for some reason. So you rewind the tape and try again. Anyway, so what we're doing is we are going to open this up and we're going to replace one of the chips in it. Oh, so the reason why we're doing that, and here's what one of these chips look like. This is called an EPROM, E-P-R-O-M. Stands for Erasable Programmable Read-Only Memory. And it's the PROM part means that you can program the chip. You can put your own program onto it. Basically, you put data onto here, ones and zeros, and then these pins on the side are used by the processor to send in an address. The addresses will be sent in as ones and zeros, across these pins, and then the program, the PROM will then go onto this chip, pull out the corresponding byte out of its memory, and send it to a set of data pins on the other side, and that will go back into the processor. So the processor will put an address to this. The address will get looked up out of here. The data will come out and go into the computer. And it's called erasable because this little window here allows the chip to be erased. If you shine a powerful ultraviolet light into this for about 15 minutes or so, it will reset all the bits on it to a 1. Just clear it out, basically, and then you can reprogram this. You use a device that looks like this to program it. So you would slip the device into the programmer, clamp it down. There'd be a USB plug here to plug it into your computer, and then it would read a data file and write the bytes to this one at a time. It would take about a minute or so to write the data to this, and then your EPROM would be programmed. And then if you wanted to change anything, you got to erase it using ultraviolet light, wait about 15 minutes, and then try again. So that's why a lot of programmers using this would keep several of these around. So while one was erasing, you could be programming another one. But I already programmed this. This is the one that we're going to install. I've already bodged on here one wire. See, the problem is is that this ROM here is bigger than and more data than the original ROM that was on here. So there's not enough address lines coming to the chip that's inside here. So what we have to do is we have to basically take some existing address lines and reroute them. Oh no, actually, not. I'm sorry, that's not the problem here. This is the same size ROM chip. I'm thinking about the RAM chip. The ROM's the same size, but the problem is that the ROM chip that's originally in here uses a different pin configuration than these more modern ones. So what we have to do is we just got to reroute a couple of the signals in order to make it compatible. It's basically a little compatibility wire. There's another wire we got to run, and that's what we're going to do on this stream today. So let's remove the power and then remove the video cable and get ready to open this up. There's 5 screws I need to undo. One right here, one here, and another one right here. 2 more. Down here. And down here. And with all the screws loosened, a couple more turns on a few of these. This lid should come off. There we go. Just carefully set that aside. And this is the underside of the circuit board. A couple of screws holding that on. So this one comes out. And this one. And we'll just carefully flip this over. Turn it around, and this is a circuit board for the ZX81. See if anyone's been chatting at me. Oh, Jordan, hello. Good day to you. I hope you're enjoying this. Okay, so a brief tour here. This has already been upgraded, but this is roughly how it would have looked. This is the RAM chip right here. This is a 32 kilobyte RAM chip. The original one was a 1 kilobyte RAM chip. And because a 1 kilobyte RAM chip will only need, let me think, 10 address signals. 2 to the 10 says 1024, which is 1 kilobyte. You only need 10 address signals, but the 32 kilobyte needs 15 address signals. And I think Sinclair kind of had the idea that maybe people in the future would be putting larger RAM chips here. So they kind of ran some of the signals to it, but not quite. And so in some cases, we just got to run some wires down to some existing traces on here in order to bring those addresses up here. And then finally, because 16 kilobytes was the maximum that this could accommodate back in the day, which only needs 14 address lines, there's enough here to do 16 kilobytes, but to do 32, you need 1 more address line, and then that's what this one is for. It's making it across the board. This is our high address line for 32 kilobytes. So without this one, we can only do 16, and with this one, we can do 32. So what we're going to do is we're going to replace this ROM chip with a new one. And, but I think I know what I want to do. See, there's a problem here, is I'm using what are called, well, let me pull this. Let me pull this ROM chip out of here. There. I'm going to use this, it's called a chip puller. There it goes. There we go. But I've got a problem here. I'm using a socket here with what's called a machined pin. So it's a round pin. And one of the things I have to do is I've actually got to stick a wire into one of these holes. And I got 2 problems. One is one of the wires I have here, they're too small. right? That they won't make contact with this. I have some other wires with me, and they're too big. So, and then these machined pin sockets are just really hard to get things into. There's a different kind of socket called a wipe socket. That's instead it's got basically two springs, and then the pin fits in between them and makes contact to it. Those are easier to work with. So I might try to get this ROM chip into here and see if I can get the wire to make contact. But I was having trouble getting this chip into here. I mean, it's really difficult to work with these machined pins, especially to insert and remove things. So I'm going to give it one more go. I'm going to try to get this ROM chip into here, and then I'm going to try to get a wire into the right spot and solder it onto that pin. Because what we're trying to do, let me see if I can bring up the right web page. Where's the web page? Here it is. Okay. So what we're trying to do is this. We're trying to make this picture here. So here's the existing wire that I've got. And then there needs to be a wire from here that goes into the socket pin where this pin was. So we're basically kind of like swapping the positions of two of the pins. So we're kind of like moving this pin over to here, and then we're moving this pin essentially down to here. So this is just like the two differences between a modern EEPROM and the old PROM chip that I just pulled out there. So what I have to do is I try to get this ROM chip into here. If I can get this into here, then I think I can get a wire into that hole there. So I'm going to try to get this ROM chip into here. If I can get it in there, I think we're good to go, because I said the wire's a little bit too big, but I think it just barely fits. If it's not going to go, then the way thing for me to do would be to pull this socket off and put a different socket on there, one of those wipe sockets, so that it's just easier to work with. So I think I'm just going to give this one more go, see if I can get it in there. So if you look at these pins, see, they're not real straight, and that's because I've been fooling around with them too much. I can try to straighten them out a bit. Just use some pliers here to gently put them back into position. Other side. Someone said here, he says, never saw someone working with a ZX81, just Commodore 64s and TRS-80s. Yeah, you know, the ZX81 was, you know, for its time, actually pretty popular because it was cheap. It's $100. You know, but by popular, I don't mean like millions and millions. I mean, you know, there were a few tens of thousands of people using them. And, you know, it accounted for a lot of people getting started in their hobby or career as a programmer. So did the TRS-80, so did the Commodore 64. The ZX81 came out in 1981. That kind of accounts for the 81 in its name. The Commodore 64 came out, I want to say, like, well, later than that, maybe 1984 or so. So 3 years after this one, and 6 years after the Apple II. So the Commodore 64 was generally a much more advanced computer, even though it had very similar specs as far as the processor and the RAM. What am I looking for? Oh, you know, it had a 64 kilobytes of memory, and I mean, this one had, the Apple II had 64 also. Oh, the Commodore 64 came out in 1982. I stand corrected then. But still, it came out after this. and it came out significantly after the Apple II. So it had the luxury of having a few more years of time to go by, where the computer industry just advanced, and the computers were just better. Okay, so what I'm trying to do, so I can get all the pins straight in there to go right into that socket. If this thing will get into that socket, and what I got to do is just gently line up all of the pins with their socket holes. And it's kind of complicated doing 28 of them at once, or 26 in this case, because 2 of them are sticking out. I'm going to use a different tip on this. Yeah, so the Commodore, I mean, I knew a lot of friends with Commodore 64s, but they got them after I got this. I think I was probably one of the first people in my school, elementary school at the time, to actually have his or her own computer. Most people couldn't afford them at the time. And, and families at the time could only really afford one computer because they cost thousands of dollars. Come on. So there would be like the family computer, which, only a few people in the family actually used. Because invariably, 1 or 2 people would hog up all the time on the computer and leave everyone else out. Oh, it's going in. I think it's going in. Yeah. So these machined pin sockets are great because they are strong, durable. They make a great connection with the pins, but they're not great for putting in a chip and then pulling it out, putting it in, pulling it out. It's really only designed to do it like once. So, in retrospect, I should have put a different socket on this to begin with. Okay, well, I got it in. I believe. What I'm going to do is I'm going to pop out this keyboard cable there. And then this can just sit right on the table. Great. I got that in. And I'm just checking to make sure. Yep, they all went in. So what can happen sometimes is you get them all lined up, like except for one. And then it gently goes into the sockets, and then that one pin gets crushed because it wasn't lined up with the socket correctly. But I think this went in pretty well. All right. And so now what I have to do, I don't know if you can see it. Here's my tool. I'm going to turn this back into a pointing tool, something I can point with. Okay, so I got the wire running from this pin over to this one. It just basically brings a ground signal, like the negative side of a battery, over to this pin here. And then this pin, which is sticking out, needs to have a wire run into the hole where this leg was. So I need to run a wire from that hole to that leg. And I can't do it with this thinner wire. This wire is too thin to go into that socket hole. But I think I can do it with this slightly thicker wire. So let's try it. Now this is actually quite a bit thicker, and I think it just barely goes in. All right, so I'm going to strip off. Can you see that? Strip off a little bit, and then let's see if it'll go in. I think I'm I'm going to need some pliers for this. And just kind of give it a little bend. So again, if you're just watching here, this is the picture I'm trying to reproduce here. It's got a wire soldered to this pin, and that wire, oh, let's try this. Here, it's got a wire soldered to this pin, and then it goes into the hole where this pin was. So right now I'm trying to poke this wire into the hole where this pin was. That shouldn't be too hard. Well, except for the fact that it's really confined quarters down there. Here, I'm going to give it almost a 90-degree bend like that so I can get that in there. Oh, is it gonna go in? Come on. You can do it. Can you see what I'm doing here? I need to cut just a little bit off of this. Make it just a little bit shorter. Just like that. Just cut about 1 millimeter off. I'm trying to put this pin in. Oh, it's going in. I need something to poke with right here. Is it? Is it going to go in? Of course, I don't want to damage the actual pin that's sitting right above it, bent outward. So I'm trying to do this. Oh, I don't think it went in. Oh, it got bent. Of course, you may be thinking like, well, why didn't I stick in the wire first to begin with? Well, before I put the ROM chip in. Well, because I didn't know if I'd be able to get the ROM chip in. Here, I'm gonna bend this pin up just a bit more. Give me a little more room. I have tried putting this in, not of course at this angle, but I have put this wire in to this socket. It has worked before. It was just a tight fit. So I hope it's going to work. Again. Oh, wait, no, just bent out of the way again. Okay. Now I'm going to try kind of a more surgical approach. I'm going to use the pliers here. Oh, come on. Oh, did I get it in? I think I got it in. Yeah. It's in enough, I think. There we go. There, that's in. All right. Now, it's a really short wire. What am I going to do here? I am going to, I guess I'm going to make, I mean, in the picture, they basically got a wire that just runs from one pin to the other. I don't think I'm going to be able to try to do that. So I'm just going to make one that's a little bit longer, maybe about this long, like that. Make that little loop, and then I'm just going to solder it to that pin. So let's clip it right there. And then I got to strip off just a little bit of the insulation. too much. That should be good. Right there. Come on. Now normally, after you clamp the stripper down on the wire, you just pull on the stripper. But I don't want to yank the wire out, so I'm going to try to do it this way. See if I can pull the wire off. That the insulation. Oh, look at that! The wire came out. Frustrating. Well, while I'm here, might as well just pull this insulation off. There. All right, let's try this again. See if we can get that wire in there. Okay. It seems so easy now. And then it's like performing surgery. Actually, it's kind of what I am doing, literally. I'm performing surgery. And then I'm going to solder this wire to that pin that's sticking out. Okay, so what I need to do to solder this, we need to get some solder onto it and then just stick them together. So first thing I'm going to do is put a little bit of flux on to both the wire and the pin. That'll help the solder stick to it, especially since I've been handling the wires, and that means it's got oils on it now, and the oils kind of prevent the solder from sticking. But here I've got some solder, got my soldering iron, and I'm just going to put, I need to take off my glasses. And glasses are for seeing things far away. This is close. Here we go. Okay, so solder on the wire. Solder on the pin. Now I just need to push the two of them together, heat them up, and that should make them stick. So I guess I'll use pliers for that. Where are my pliers? There they are. There, they're stuck. All right. That should do it. Looks like I could add some more solder, but that would risk them coming apart. Well, that should be it. That should be the surgery. So before we put it back together, what do we got here? We got the processor. This is the Z80 processor. RAM, 32 kilobytes of RAM. The ROM, this is this new one. Oh, what does this new ROM do? So this new ROM fixes a couple of bugs in the existing ROM, and it has sped up some of the routines. So, like, there was, if I can remember what this one does, there was a math routine. A couple math routines are now faster because either they found faster ways of doing it, or just whoever program rewrote the routines for it just knew of a faster way to do it. But apparently the square root function is now a lot faster than it was before. And also some of the other trig functions are faster. And also there was a instruction called pause that was used to make your program just pause for a moment. That, I think, caused a little flicker on the screen when it did that. And this ROM fixes that flicker. So those are the primary fixes with this. So we're going to try it and hope it works. I've never done this before. And if that'll work, then I'll cover up this little window because I don't want to erase the program accidentally. And then the mod on my original ZX81 will be 90% complete. The last mod that I would do, which I don't have the parts for today, but is to get one of those ESP2 microcontrollers, the really cheap, like a sub $10 32-bit microcontrollers that's got Wi-Fi, Bluetooth, and 4 megabytes of RAM. I mean, these little, it's amazing. You can get little computers now for 10 bucks that could run circles around this old computer. In fact, you could run a program on those new computers that would emulate all the hardware of this computer and still have processor speed to spare. Anyway, you get one of those, and you attach it to a few of the pins here, and it will do a couple of things. One is it will take the composite video signal coming out and turn it into a VGA signal that you can connect to a modern monitor. And it will also connect into, I think, the earphone and the microphone ports of this, so that you can upload a program to that microcontroller, a Sinclair ZX81 program to it, and then just say load, and it'll play it back into the earpiece port really fast into this. And so your program will load in just a couple of seconds instead of a couple of minutes like it would before. So you can basically use that ESP2 as a virtual set tape in which you can store multiple programs on it and then just load it whichever one you want. So that's another project for another time. And that one only needs like 3 or 4 extra parts. And then of course that microcontroller and a couple of wires to run things too. And then you just need a VGA port. Stick it somewhere on the back of the computer or hanging out the back or something like that. And then you'll have a ZX81 that can connect to a modern VGA monitor. Oh, so what do I want to do? I want to connect up the keyboard. Actually, before I connect with the keyboard, let's just connect up power and video and see if we get something. This will run even without the keyboard connected. We don't be able to type anything, but at least we'll be able to see if it works. So let me turn on the monitor. And this is going to be very anticlimactic if it does work, and it's going to be kind of disappointing if it doesn't. So here we go. There we go. It works. We got our prompt. That K prompt there means we're ready to type in a command, like print or a line number. So the ROM is working. That's good news. So let's disconnect the power and then put it all back together and see what we got. Keyboard cable number 1 goes in right here. These are very flimsy cables. This is actually a modern replacement for the original keyboard. The original keyboard, this cable basically disintegrated. Every time you handled it, it would crack. And then it finally just broke. So there are people making modern keyboard replacements. Looks just like the original ones, but has a much more durable, flexible connector. Still a flat membrane keyboard. Still takes just as much effort to type on it. It's just a modern replacement. About $10. Okay. Do that. That over. Make sure my bodge wires aren't through the screw holes like they were before. Now, where are my screws? Huh. Where did I set those? I know I set those in here. There they are. I have taken apart, put together this little computer so many times. When I was a kid, after I'd used the computer for a little while, probably, not very long, a couple months, took it apart. See how this thing works. Oh, there's not much in there. I was too young really to know what all it did. I said, oh, there's 4 chips in here. Interesting. Put it back together. take apart the RAM expansion. Oh, look, there's 8 chips in here. I wonder what those do. I had no idea back then. If I knew then what I've learned since then, life probably would have been a lot different. All right. Here goes the video. And power. Let's switch over to the TV again. Bingo. All right, let's see. 10, print, blue. Oh, did you see that? Did you see how fast that was? I don't know if you remember. When I press enter, there'd be about maybe a 1 second blank before it displayed the program. That's been sped up tremendously. Let's run this program. Wow, it's so much faster. That is amazing. Whoever fixed those ROMs was, kudos to them. Let's try this run. Boom! Wow. I had no idea this thing was going to be so fast. Well, I mean, like, comparatively speaking, still slow. Right, let's try that loop. Let's go. Let's take out line 20. 20 gone. 20 for x equals 1. So, I mean, replacing the ROM did not, I didn't make the processor faster. It's just the routines that are in the ROM now have been optimized. 30, print, x, 40, next, x. You know, when I first got this computer, and I was looking for the various commands, like, you know, plot, print, next, for. I'd have to scan all over this thing looking for them. And some of them were kind of easy to remember, like P and print. You know, they both start with P, so those are on the same key. And also the quotation mark is also there. So everything, almost everything you need to print, except for the words itself, are just right there. And then, you know, R for run, and S for save, L for let, which is how you assign variables. So, you know, a lot of them kind of made sense and they were easy to remember, but I would just go scanning around and around. And then after, you know, a few weeks of using it, you just kind of learn where the commands are. And I didn't think that muscle memory would come back so fast. I mean, I just got this ZX81 working again for the first time just a couple weeks ago. And then I set it aside. And then because I didn't have all the parts to do all the upgrades. So now I've got all the parts to do the upgrades, and I'm finishing the upgrades. And it's just amazing, like, how fast it is taken, how short of a time it's taken for that muscle memory to come back, where I just don't have to hunt around as much anymore to where those commands. I just know that next is on N and 2 is on 4, print is on P. Anyway, let's run this. Wow. Remember, that loop took like 10 seconds to run before, and now it takes just like 2. It's much faster. And then we didn't run a program that uses square root, but apparently that's one of the things that was really sped up. So let's list the program. Gosh, it is so fast. We'll go 30, print, x, and then to do another variable, I think it's a semicolon, not a comma, semicolon, and then let's put in a space, and then a semicolon, and then we'll do square root. Where's square root? Now that is something I don't necessarily know because I never used it. There it is, square root. It's on H. So to get that, we're going to go Shift Enter, which is function. You can see the cursor changes to an F, and then we press. There we go. Square root we'll run that. Now, I don't know what it was like before. I mean, first of all, the loop, remember, took about 10 seconds to run, and this one only took maybe 3 seconds this time. And so that means that square root routine is slowing things down a little bit. But from what I hear, this is a lot faster than it was before. The square root was really slow, and now it is much faster. That is amazing. So, how do I, here's new, that's what I was doing. Oh, so, you may be wondering, what are these like, when I hit plot or print, what does that mean? So when a basic program is entered into the computer, the keywords like print, go to, for are actually stored not as the letters FOR for or PRINT for print, but as just what's called a token. It's a single byte that just represents that keyword. So the way BASIC works is the keywords are stored as those tokens. So when you type in a program on a traditional like Apple computer or Commodore 64, you type in 10 print quotes, hello quotes, and press enter. That print gets interpreted, it gets recognized and then stored in memory, not as those 5 letters print, but as the 1 byte that represents the print keyword. And there's a table somewhere that tells the computer what all the different keywords are. So each one of these keys on this keyboard represents one of those tokens. So print is a token, poke, input, if, return, random, run, those are all tokens. All these words here are represented in the computer, in the program memory, as just a single byte. And so what Sinclair did, the maker of this computer, was just assign a key to each one of those tokens. So when you press, let's say print, P for print, it displays print on the screen, but it's only storing that one byte token in the program. Other than the tokens, pretty much everything else is just stored as bytes, stored as is. Even numbers are just stored as a kind of an array of ASCII characters, array of digits. Variables are just stored as the variable itself, not the address of the variable. So nothing is done to like optimize the program except for storing the keywords as tokens. What that means though is, for something like Sinclair, it can kind of do basic kind of rudimentary syntax checking as you enter the program, because you have to type keywords when you're supposed to type keywords, and you can type in functions when you're supposed to type in functions. Like a line number can't start with a function name. It can't start with like random, but it can start with print, and then print random. That works. Like print out a random number, but you can't just start a line number with a function. You have to start with one of these keywords, and so that's what that K word actually means. It says it's accepting a keyword at that point. So even programs like machines like the Apple II, the Commodore 64, they work the same way. You type in the keyword, but then as it scans your input and turns it into the basic program, it turns those keywords into the tokens themselves. So what I guess what I can do here is type in one of these programs, and I typed in one of these the other day. This was one that it printed an oval on the screen. It was really slow. Oh my gosh, it was so slow. Just to put a circle on the screen. There we go. The program. Oh, the program here to print out an ellipse, making an ellipse on the screen. So I'm going to type this in, and I'll see it go. So you're going to have to look at this horrible screen. But I'm going to type this in. So let's see, we did a new, right? There's no program there. So we're going to go, I'm just copying this. It says here, 1 print A equals semicolon. 1 print, oops, quote. And this is the other problem, is I'm holding this book open with one hand, and I got my other hand typing, and sometimes I need to press shift, so I actually need to, set the book aside. I don't know how I'm going to do this. Yeah, I'm going to do it like this. Boy, if I could get somebody to hold this book open for me, that would be fantastic. I am going to set my Palm programmer right on that, and I'm going to put the computer on here, and there, that'll work. Okay, so one, print A equals quote semicolon, enter. Fabulous. 2, input A. 3, print. Now, one of the things I liked, in retrospect, go now 30, 40 years later, one of the things I like about BASIC was, well, first of all, it's really easy to get into, right? You just read what you see printed here and you just type it in. The other is the line numbers, although they seem antiquated by today's standards, really kind of reinforced to beginning programmers that this is the order in which the statements are going to execute, right? They're going to execute in numeric order. So you learn that there's sequences of statements that start from the top and work their way down. And then when you hit something like a goto, it's going to stop what it's doing and resume execution on some other line number. So the order of execution was really explicitly written out in the program. And I as a teacher, I run into students for whom they don't quite understand that programs are executed one statement at a time from top to bottom. Of course, there's loops and conditionals in there, but basically from top to bottom, and they're done sequentially. I've seen some students come to me and say, like, I don't understand why my program's working, because somewhere in their mind they're thinking all these statements are being executed not sequentially, but kind of like simultaneously. Right? The whole thing is running all at once. And maybe because computers are so fast these days, you kind of think that that's happening because it happens so fast. Whereas on this computer, it's so slow, right? You can literally see each line being executed as it's going. You can see that it's executing it definitely in order. But that's one of the things that line numbers are kind of good at. It's just reinforcing this idea that programs execute sequentially from top to bottom. Okay, where am I? So this little b here means I'm going to put a space there, a blank space. B equals quote semicolon. The semicolon on the end of a print just means don't put the cursor on the next line. Leave the cursor where it was. Okay, 4 input B, and then 5 print B. 5 print B. Okay, so that basically inputs the two parameters A and B into this program. Now I'm going to go into a loop. It says 10 and 10 for Q equals 0 to 360. For Q equals 0. You can see that what it's doing here is it's going to go around a circle 1 degree at a time. So if you're familiar with your trigonometry, we're basically going to go through a circle, and then we're going to use some trig functions, sine and cosine, in order to calculate the distance from the center. Let P, whoops, I need a line number on that, 20. This is an assignment statement. Let P equals Q times, and now I need pi, which is right here. It's the symbol pi. That's a function. So shift, enter, puts me into function mode. And then instead of displaying the symbol pi, it puts out the letters pi. And then divide 180. And then 30. We're going to plot, which is going to put a little black square at these coordinates. A times parentheses 1 plus cosine of P. 1 plus cosine. Cosine's over here. Cosine P, comma, B times 1 plus sine of P. E times parentheses 1 plus, forgot where plus was, there it is, plus function sine P. Well, that took like 2 minutes to type in that one line. It's all because I can't do any touch typing here. 40 next Q. Right, that's my program. That's the whole program. Run. Okay, so A equals, and my input is down at the bottom. It never does input up at the top of the screen. It prints stuff at the top of the screen, but input is always done at the bottom. Let's do 30 and 20. So we'll do 30, and B is 20. And here it goes. It's not much faster. This part's not much faster. It may be a little bit, but see it crawling along, making its oval. Once I get that mod done to get VGA output from this, or when I plug this into one of my scan converters, the video will be a lot better. It won't have these dancing lines on there. So that's just caused by a mismatch between the scan frequency of the TV and the scanning frequency of the camera that I'm used that's aimed at the TV. But if I can get that video input straight into the computer without going through a TV first, and going through a TV and a video camera, the wavy lines will go away. All right, I have to say this is a little bit faster. Maybe twice as fast as it was before. But still, I mean, nothing like today's computers. Today's computer, you say, put an oval on the screen, and bam, there it is. This one, not so fast. All right, we're halfway done. Just going to go around and do the other half of the oval. Now, I remember typing in this program as a kid, and you know, I recognized it was slow, but it was like, wow, I just got to draw a shape. Computer can draw a shape. That's amazing. Now, one thing that would speed this program up a lot is not looping from 0 to 360. Because you're basically you're doing 1 degree at a time, but those pixels that it's drawing are bigger than a degree. So if we could get it somehow to like calculate how much to jump by, then it would only have to plot the pixels that it needs to plot. Right now, what it's doing is, because the degrees are going, or there's more degrees than there are pixels, so those pixels are getting written multiple times to the screen. So we're doing extra work. There. Program's done. How long did that take? 5 minutes? 4 minutes to draw a circle? And look at the program. There's also some stuff in here that like could be fixed. Like, for example, line 20 there, it's basically converting degrees to radians. And maybe if there was a way to count in radians to begin with, this could go a bit faster. What else could we speed up? I'm not quite sure how modern computers do it to draw circles so fast. One of the ways they might do it is, rather than like doing this trig every time, is instead kind of like going scanning left to right, making a rectangle, and just going basically, is this pixel on the circle? Is this pixel on the circle? Is this pixel on the circle? So you just basically, instead of scanning from 0 to 360, you scan through all the pixels and just determine which of the ones you should turn on and which of the ones you should turn off. So it paints the picture from top to bottom rather than as a circle, I think. one way to do it. Plus, if you recognize, if you're doing like circle drawing routines, you might recognize that circles are typically symmetrical. So anything you do on one side, you also do to the other side. So you can do 2 pixels at once. So instead of going from 0 to 360, we could do this from 0 to 180, and then just mirror whatever we do to the other side. We'd actually just do 1 to 0 to 90, and just mirror it 4 ways, and that would work. That would make it a lot faster. All right, I am super happy with this upgrade. That has now turned my ZX81 into a turbo computer. Turbo. So hopefully on some other stream I will be showing, like, I'm going to order those ESP32 boards, and the parts needed to hook them up so that we can hook that up, put it into the case, and then somehow have a VGA connector coming out. I don't want to damage the case too much, right? Because this is a vintage computer. Well, what I could do is I have 3 others of these. Sinclair was the British brand, and then you know, when I ordered it, it basically came from the UK, but Sinclair sold the rights to the computer to be sold in the United States under the Timex brand. Timex, the ones that make watches. And so that's the Timex Sinclair 1000. Exact same case, except that it's got Timex Sinclair up here and the number 1000, and the ZX81 is not here. But when you open it up, it's a ZX81 on the inside. It actually says ZX81. In fact, here's the board for it. I started taking it apart, so I'm going to start modding it as well. Set this aside. Here's the Timex Sinclair 1000 and all of its little parts. So I've taken apart the RF modulator that transmits it on channel 2 or channel 3. I gutted it, took out the board, and all we're going to do when this is done is just run a single wire from the main board to the RCA jack on here. That's all that's going to be inside of it, and then that'll go back on the board right here. I'm going to put in a socket, and then that new chip that you can get for about, I think they're about $35, that replaces this old one that, first of all, I think has some bugs in it, and second of all, they just tend to go bad. I guess they were not, you know, they were not, how shall we say, high quality components. And so after about 10 or 20 years, these chips would just go bad physically. Something inside would just break. So people tend to just pull those out, put in a modern replacement that can do the composite video and fixes some of the bugs, and then also upgrade the RAM. So I'm going to put in a socket for that. Do the exact same upgrade to this that I did to the other one, and I'm also going to put in a new power regulator. So I took the old one out. The old one was a 7805 linear regulator, and the way those regulators work is if you put in excess voltage, first of all, they take a DC voltage like 9 volts or 12 volts or 15 volts, and they step it down to 5 volts. And the way they do that is they shed the excess voltage as heat. So if you put in a 9-volt signal in here, 4 volts have got to be dissipated. And so there used to be a large aluminum heatsink that it was attached to right here. It's about 2 inches square, and it would just shed its excess voltage as heat. And you can feel it on the computer. You put your hand on the keyboard right in that area, it kind of gets warm. These days, you can get these little boards like this, and this is a modern switching regulator. So it can take the voltage up to about 15 volts and step it down to 5 volts and do it very efficiently. It basically does it by switching the voltage on and off really, really fast. And so if you take, let's say you put 10 volts in and you switch the output on and off really fast so that it's 50% on and 50% off, so half the time it's on, half the time it's off, that averages out to 5 volts or half the voltage that you're putting in. So these things run much cooler, they can handle more power, and they only cost like $1. So I'm going to take the old 7805 regulator out, which I already did, and I'm going to put this new one in right there. And then I'm also going to replace these capacitors. These tend to go bad as well. They just there's a liquid inside of them that's used to make them work better, and that liquid kind of dries up over the years. These styles here don't go as bad as like the early surface mount ones, but while I'm at it, I'll replace these two. So RAM upgrade, glue logic upgrade, ROM upgrade, replace the capacitors, change the composite video output, replace the voltage regulator, and then we'll have another computer that works just like that one we were just using. Faster, better, and what was I going to say? Oh, for that one, that's the one that I might do like a VGA mod to, because I can modify the case. I don't want to touch like the case of my original computer. What is that, 30, 40 years old already? And this one here also dates from the same time. Actually, you can see right there, Sinclair ZX81. So even though this was a Timex Sinclair branded computer, it's just a Sinclair on the inside. Right, so that is what I'm going to do. You guys have been kind of quiet. You guys have any questions? Well, I think what I'm going to do is wrap up this stream. I've done what I wanted to do. I'm going to have a little fun programming my computer. I'm going to type in some old programs that I used to do, like that duck hunt one. I might try to do that one. And yeah, that's it. Well, have a good day, everyone. Hope to see you soon. And next time you see me, I'll probably be doing more of this retro computing modding. Kind of fun to get these old computers working again. Okay, folks, take care. Have a great day. See you all soon. Bye-bye.